Hello everyone, welcome to my talk. My name is Kunbei Cai. I'm a PhD student in ECE at UCF. Today I'm going to present our paper, NMT-Stroke, Diverting Neural Machine Translation through Hardware-Based Faults. This work is done with my advisor, Dr. Fan Yang, and in collaboration with the Clemson University. Today, numerous natural language processing applications are employed in critical systems, and their security attracts more attention. Many prior studies mainly focused on investigating external threats for machine learning, where the attackers temper their inputs to make the model misbehave. However, recently advances in hardware-based attacks such as Rohammer, overclocking, and voting demonstrated severe security issues in computing systems from internal threats. This study has highlighted the importance of understanding the impact of hardware vulnerability to the integrity of emerging applications. Unfortunately, the security of NLP models from the hardware perspective has not been well explored. In this work, we aim to perform the first study on hardware fault attacks against modern NLP models. Specifically, we focus on neural machine translation, or NMT, which is one of the most critical NLP tasks. The attack can be described as follows. First, a victim deployed a pre-trained NMT model from a trusted site to a remote infrastructure such as the cloud. We assume that attacker also has knowledge of the model information, and he will temper the translation by inject faults to the model parameters. In particular, we are interested in understanding whether the attacker can hijack any benign input sequence to one attacker-controlled output sequence. Although the attacker objective is straightforward, we notice that attacking NMT exhibits some key challenges. Prior work have shown the success of 14 SM-based classifiers through flipping the most significant bit, or MSB, to drastically degrade the model predicting accuracy. However, different from classification tasks, the natural language output sequence of NMT models is subject to human judgment, such as fluency. Therefore, naively faulting the MSBs may lead to unnatural sentences that can be easily identified by a human inspector. For instance, the following figure shows an example translation from a transformer-based NMT model with one random MSB bit flip of a model parameter. We can see that the output consists of repeated words without concrete meanings. To solve this problem, a more effective fault injection strategy had to be employed. Now we present the design of the bit identification algorithm, which is named as value-aware gradient-guided bit search. The goal of the algorithm is to find the least amount of model bits to flip, and to achieve the attack goal, we design an iterative search process that optimizes the loss of the network towards diverting the output to desired sequence. For each iteration, the algorithm locates the top n model parameters with the largest absolute value and the top n parameters with the largest absolute gradients. We then find the most vulnerable bit for each layer from the combined set based on its impact to the translation output. After that, we rank those bits across all layers according to their loss drop and identify the top bit as the next flip target. We continue with this iterative search process to locate more bits to fault until the attack objective is satisfied. To ensure the identified bits are exploitable in real system, we instantiate NMT-Stroke by modeling the Rohammer fault vector. First, we perform a memory templating that collects faultable memory location in the targeted DRAM system, called bit flip profile. Second, NMT-Stroke model Rohammer attack by integrating the bit flip profile as the bit search constraints. With this, the candidacy of the targeted bit also depends on whether its page offset matches a certain DRAM zone. Such step ensures the identified bits in memory can now be precisely flipped in real system. Note that prior techniques by Yao et al. Has already shown possibility of multi-bit flip through deterministic multi-page Rohammering. To evaluate the effectiveness of NMT-Stroke, we configure the state-of-the-art transform-based NMT models, including T5 and Opus NMT, with 3 language pairs. To quantify the success of the attack, we first use the bilingual evaluation understudy, or BEU metric, that evaluates the closeness between the tempered translation output and the attacker-controlled reference output. Additionally, we also consider the exact match rate or EMR, which defines the ratio of translation instances where the exact adversarial translation is generated. The stop criteria for the bit search is when the BRU is greater than 85 and the EMR is greater than 90%. Finally, we randomly select one sequence in the dataset as the attacker-controlled sentence. We evaluate NMT-Stroke, and the results are summarized in this table. First, we can see that NMT-Stroke can hijack the translation of all the NMT models successfully according to the attack objective. In particular, the number of bit flips required is considered the modest in the range of 39 to 79. Additionally, by modeling the hammer constraints to ensure fault exploitability, we observed a slight increase in the required faults, specifically from 48 to 93. We noticed that such a difference is due to the imposed constraints that may disqualify a certain vulnerable bit to target, as it is not hammerable in real system. Overall, we find that NMT-Stroke is still effective in compromise all configurations under study. To understand the generality of our proposed attack, we further perform a sensitivity study to understand how the targeted sequence length and content influence the effectiveness of NMT-Stroke. In the top table, we can see as the length varies, the bit flips needed can change considerably for both models. We identify that the output length is a key factor to influence the success of NMT-Stroke. We further varies the content of attacker's desired output sequence with the same length. The bottom figure illustrates the distribution of required bit flips for 3 NMT models. We observe that the number of bit flips exhibits large fluctuations. However, NMT-Stroke is still effective in achieving the attack goal to all sequence instances. The study reveals that the selection of the attacker's controlled sequence can indeed have non-trivial impact on the effects of the attack. Due to the limit of presentation length, we encourage the audience to check more details of our proposed work in the paper, including a fine-grained bit flip characterization in NMT models, the detailed algorithm formulation, and a summary of major takeaways for future mitigation. Thanks. Have any question?